Hello again. My name is Shokhrukh. So let's analyze part B and part C of question number 2. In the previous video I told you that I won't analyze them, but I said that it's pretty really simple, and I do hope that before starting this video you tried solving it yourself or understanding it yourself. So if you didn't do it yet, so just please do it for now. Just pause this video. Actually, part B and part C are very simple, especially part B. If you remember, in part A we did BEQ instruction. BEQ instruction means branch. BEQ means branch when condition is met. So when some specific condition is satisfied, we're gonna do branch. Branch means jump. There are two types of jump: conditional and unconditional. BEQ is, as you might know, as you might have understood, conditional jump. Simple jump is unconditional jump. It means doesn't matter if condition is met or not, whether there is a condition or not, you're gonna do jump, okay? Simply jump, okay? So in part B, we're gonna do this simple jump, unconditional jump. There's no condition to check. We jump. For example, see, what we do is the same. I mean, PC target. I mean, we're just getting the value of target, putting it inside or into PC program counter. Here also we did the same stuff, but please be careful. Here we had this if condition. Only if this condition is satisfied, then we did this one. But here there is no if condition. So the task is the same. We're gonna write the values of control signals for this instruction. You know, as I've told you, as I explained to you in 40-minute long part A video, that while executing any kind of instruction, this control will send signals to parts, to blocks, okay? As you know, in the processor, there is control part and data path, okay? This control sends the signals to special or particular parts in this data path, this data memory, to LU, to registers, and so on and so on. So now we have to analyze what kind of signals and what kind of values of the signals this control block will send while executing simple jump, unconditional jump. So please firstly see that this is J-type instruction. So before going there, I'm gonna delete this stuff because you're smart guys, you know, you watched part A, so everything's clear. So see, in the previous video we worked with I-type, now we work with J-type. So see, in J-type there's nothing actually, because you know in I-type we had this RS and RT because we needed to compare them so that we will know whether the condition is satisfied or not, whether they're equal or not. But in J-type we just jump, there's no condition to check. So those we have just opcode which says we're not interested in the value of opcode. This opcode just says that we do jump. Just know that we do jump. That's done. We're not interested in the value of opcode. We don't need it actually. And the immediate of value is probably just zeros, only 26 zeros or 26 ones. We're not interested in the value of immediate because, you know, we don't use it, we don't need it. We just jump. We do just jump operation. So, you know what does it mean jump? What does it mean jump? Jump means, for example, this is your code, this is instruction. Now your program counter PC points this stuff. So the next instruction is, if it's current one, the next instruction is this one in a normal way, in sequential way of program execution. But if you do jump, you just update the value of PC so that, for example, you then after this case, after this one, you execute this one, okay? So in order to do that, you have to change the value of program counter, and this is what we are doing. This is a target. This is a target. And address. So putting this address to here so that program counter will not point to this stuff but to this stuff, okay? So I explained to you the meaning of this PC, left arrow, and target. So now let's analyze the control signals. why, for example, there is don't care, why there is 1, why there is 0. Okay, so firstly, if you remember, I've told you that if branch is 1, jump is always 0. Okay, in this particular case, jump is 1. Okay, jump is 1. So if jump is 1, that means we're not doing branch. Okay, and see, we're not interested in the value of branch, because we are anyway jumping. What I mean, branch is what? You jump when some condition is met. In jump, you jump without looking at the condition. So we're not interested in the value of jump. Whether it is 0, 1, anyway we jump, nothing can stop us. So that's why I'm putting 1 to jump, because we are jumping, and I'm putting the value don't care to this branch, because we're not interested in the value of branch. Okay, we don't care about it. So again, I'm just putting don't care to X. If you want to know about everything about why registered destination is X, or why it's X, what does it mean actually registered destination, what does it mean this stuff, please watch part A, watch the video 1. So why a registered destination is don't care? Because we are jumping, we're not interested in registered destination. Registered destination is going to be 0 when we store something in register, when we take some value from the memory and put it into the register. In that case, or take some value from the instruction. Okay, for example, here in the instruction we are getting the address, we are getting the value in the register, and if you update some register, if you put this value inside the register, then our register destination is going to be 1. Register destination is going to be 1 when we store something in register. In that case, we are just jumping, we're not storing anything inside the register, so it's going to be don't care. In the previous video, I told you that these blocks can't receive don't care signal, they receive either 0 or 1. Only this multiplexer can receive don't care. Okay, so branches don't care, register destinations don't care, memory read is don't care, memory to registers don't care. Why? Memory read, no, stop. Memory read is not don't care, it's 0, because it is coming here and getting to this block, the data memory, it can't receive that. Okay, it's gonna be 0 because we're not reading anything from the memory, we're just jumping, so this is 0. And memory to register is multiplexer, right? Yeah, multiplexer. Memory to register is what? Take something from memory and put it into register. We're not doing this kind of stuff, we are just jumping, so that's why it is don't care. LU opcode is what? The opcode is the value from which ALU identifies what kind of operation it will execute. In this particular case, this is going to be 2 don't cares, because ALU opcode is 2-bit value. See here, opcode is 2-bit value. In the previous video, I explained it more clearly in details about opcodes, about ALU, everything. I've analyzed it, not only just part A. I just explained everything, how this functions. So just watch the first video. But in this case, ALU opcode is going to be don't care to access, because we're not executing anything, we are just jumping. We don't need to use ALU in this particular case for unconditional jump, because we don't check any kind of condition. In the previous video, we checked the condition by subtracting, but in this case, we're not doing it. Okay, so 2x's, so xx. So memory write is gonna be what? This memory write is coming here. This is signal sent to this block. It's gonna be don't care. Why? Because as we are not writing anything into memory. Okay, memory write is gonna be what? When you take some value and store it in memory. We're not doing that, so it's gonna be 0 signal. We're gonna send 0 signal because we're not working with writing memory and this kind of stuff. To access 0. LU source. LU source is gonna be, I guess, don't care, right? Yeah, don't care. Because what does this LU source actually mean? Okay, again, I tell you, if you watch the first video, LU source is responsible for the second input to the ALU. For example, if if LU source of selector is 0, we are getting the second operand from the instruction and putting it as an input to the LU. If it is 1, we are getting the immediate from this range of the instruction sign extend. Oh no, sorry. Why I'm coming here? Our immediate is 16-bit. We are sign extending it into 32-bit because MIPS architecture, MIPS machine is 32-bit machine, and putting this immediate as a second operand, second input to ALU. You know, our ALU, what kind of operation it does? It does XX. It does. I mean, it does nothing. You know, we are not using ALU, so we are not interested in the input of ALU because, you know, we don't care whether it is this one or 0. I mean, whether this is a second register or whether this is immediate. I mean, sorry, not this one, but this one. We don't care because, you know, we don't use this stuff. Okay, that's why. Let me delete everything. But that's why this ALU source is also 0. Okay, I mean, this multiplexer, the selector for this multiplexer is not 0, but don't care because we're not interested in the value of the selector. I mean, we're not interested in this stuff. You know, we select using this ALU source. We select this one or this one. We're not interested in this one because we don't use ALU source. Okay, so that's what ALU source is. Don't care. And register write is 0 because register write means what? We write something to register, take some value from instruction and put it into register, or take some value from the memory and put it into register. We're not doing this kind of stuff. We're just jumping, so that's why we send 0 signal to this block. We can't send don't care because just you can't send don't care to the blocks, combinational blocks. So we set the register write to 0. As you can see, 0. Sorry, as you can see, 0. And finally, we have left this PC source 2. PC source 2 is what? See, PC source 2 is branch taken. You know, PC source 2 equals to the value of this AND gate, and the first input is branch. The branch is don't care. That's why the outcome is don't care, because if either second input 0 or 1, the output is gonna be don't care because we are not branching. PC source 2 equals to what? Actually, PC source 2 is equals to branch taken. What does mean branch taken? It's gonna be PC source 2 is gonna be 1 when branch is taken, when condition is met. When condition is met, when we jump it after satisfying condition, we set PC source 2 to the 1. If not, I mean, if condition is not met, we set it to 0. In this case, we're not doing branch operation. We're not checking anything. That's why branches don't care. That's why the outcome, the branch taken, PC source 2 is also don't care. Okay? Yeah, this one. So everything is simple. And now you're doing R-type instruction. You're doing add operation. Let's say you're doing this one. And C. I'm not gonna do it for you. You have to do it yourself because you know everything. You know how this single cycle MIPS architecture works. In this case, what does this mean? You just store in RD address, okay? In RD address, the summation of the value inside RS address plus the summation of the value inside RT address. I mean, this is a address pointing to the registers. You store it here in this address. So for this you use R type, and you know why R type? Because you need 3 addresses. Yeah, here. This is the first operand, this is the second operand. I mean, the address of the first operand, address of R1 is this one, address of R2, okay, let me put it here, address of R2 is RT, and the address of R3, where you're gonna store the summation of R1 and R2 is RD, okay? So unit 3, what does mean? 3 parts in the instruction and 3 addresses, so this you use R type. And everything is simple, everything is simple, and You know why? Because you add just two registers and store it in third register. So this register destination is gonna be 1 because you are storing. You are storing, as I've told you, register destination is gonna be 1 when you store something in the register. So it's gonna be 1, and the register write is gonna be 1 because you know why? You write value inside the register. Okay, you write the value, the result of RS. I mean this one in this RD address, which is what pointer to some register. So you're writing something, you're storing something. Okay, so this register write is 1, and you know, memory. You know, let's do it till the end. Branch is 0 because you're not doing jump. Memory read is 0 because you're not reading anything from the memory. Okay, this address is just the index. Let's say this is the index of the register. Okay, for example, you see you have, let's say in a MIPS architecture, I guess you have 32 registers, but let's say you have 7 registers, and you know, in order to identify which register you wanna access, you know, you do what? Indexing from 0 to 7. So this RS and RT are just the value of these indexes, and the size of RS and RT are 5. I mean, from 25 to 21, this is RS, and so on and so on. From 2016, it is RT. You know, this is 5 bit. This is 5 bit because in this MIPS architecture, you have 32 registers, which is 2 to the power 5, right? To represent, to index these 32 registers, you need 5 bits. It's simple. So this is the meaning of RSRT. Okay, this is not the value. This is just the index. So this RS means access register RS. For example, if RS is 2, that means first operand is R2 plus. If let's say RT is 4, that means you access R4. I mean, not R4, but this one. Okay, a register at index 4. Okay, let's say it here. And the store result in register with index RD. Okay, so this is how everything functions. And you know, here you send this from 25 to 21. This is the index of the first operand. Index of first operand, RS index. This is the index of the second operand, RT, and this is the index of RD. This is gonna be 1. I mean, which is register destination is gonna be 1 because we are storing something in register. So then this combinational block, this block does what for you? This block just puts the value of the register with index RS. I mean, this equals to then read data 1. Actually, this one equals to then R register at index RS. Okay, and this one equals to register at index RT because you know we gave RT index RT. This block, this magic block, okay, gets for you the value of the register at index RT and puts it here, which is gonna be actually finally the inputs to the LU, and LU does what then? It does plus operation RS. I mean R at index RS and R plus. I mean plus R at index RT, and the result finally is gonna be then going to some let's say register. Let's say is register which is at index RD. Okay, RD given here. So result comes here. I mean, result comes here. This is the result coming here. Write data, and this block, combination block, magic block, then gonna write this data inside this index. I mean RD. Okay, RD at this index of the register, it's gonna write the final value. So everything is simple. So you know everything. So we're not accessing memory, so it's 0. We're not accessing memory and putting some value from memory to register, so it's 0. We're not writing anything to memory. We're not storing anything into memory, so this is 0. LU source is 0 because you know. Actually, I am doing also part C. LU source is 0 because you know. Let me delete it. as I explained to you in previous video, LU source is gonna be 0. It means we are taking the second operand, second input of LU from this block. Okay, actually we have to take from this block because we gave RT, index of second register to this block. So that means we have to take it from here. So that's why we put 0 to LU source. If LU source was 1, that means our second input to the LU is our immediate, this one. But this is not the case. Our second input to LU is the second register, so that's why LU source is 0. And yeah, what's left? PC source 2 is 0 because branch is 0. Okay, branch is 0. And PC source 1 is 1. PC source 1 is 1. And this is because this is because our jump is 0. I mean, why jump is 1 here? Our jump is 0. We're not doing jump, so that's why jump equals to PC source 1. So those we're not jumping, we're adding, right? So this PC source 1 is 1. No, 0. So we're left with this LU op. LU opcode is 1 0. I guess you just understood everything, right? You know, a major principles of working control signals I explained in the previous video. So that's why I explained this part B and part C maybe a bit fast. So please watch first video and revise everything. And then everything here what I've discussed would be clear for you. Now I'm gonna finish this video with discussing LU op. This is gonna be what? It is 1 and 0. Let's see the table. 1 and 0 is operation which is controlled by the function. Okay, what does it mean? It means that we specify the operation by the function which is passed in our instruction. So actually, maybe you thought also, like me initially, that our LU opcode would be 0 0 because we are adding RS plus RT, right? They're doing plus operation, which is addition, which is 0 0. No. You can't do it, and let me explain. Because, you know, the opcode you have to specify in the instruction, right? But please look at R-type instruction. The first 6 bits which have to be opcode are 0. I mean 0 0 0. You know, 0 means nothing. Here we can't understand, or we can't derive what kind of operation we're gonna do based on just zeros, you know. For example, this 0 may be just branch, this 0 may be jump, this 0 may be addition or subtraction. We can't just derive from just 6 zeros the type of operation. So that's why in R-type instruction, the operation, the opcode, or operation, and that's why LU opcode is controlled by this function. Okay, 6-bit function. So that's why in R-type, again I'll tell you, operation is controlled by the function, the least 6-bit function, 6-bit from 0 to 5, because our opcode is 6 zeros. Zeros mean nothing, because this 0 may be, these 6 zeros may represent add, addition, not addition, subtraction, multiplication. We don't know. We don't have information, you know. That's why we specify our operation by this function. And in order to say to this LU, let me delete this stuff, I guess you know, to specify, oh my god. You know, our LU should also know what kind of operation we are executing, right? Because, you know, then it can't execute. If it doesn't know what operation we do, it can't do anything. So now we have to say that to this LU, to this LU that our operation is not kind of add, addition. No, our operation is controlled by the function. To explain it, to say it, to let LU know, to inform LU about it, we specify this LU opcode to be 0 1 0, because 1 0 means that the operation is controlled by the function specified in this case here in R type, the least 5 bits. And when LU receives this 1 0, I also explained it in the previous video, it will look up inside LU. There is a table. It will look up to the table. Here there are opcodes. Here are the operations opcode. Okay, opcode. This is what but LU receives. And looking at this opcode, it specifies the operation. This is operation. Okay, so here there is 1 0, and here it's written that it's func. When LU receives 1 0, it will understand that, hey, now I'm not gonna do plus, minus, or multiplication. What I will do is specified by the function, which is at this index, right? At this index, at this range. Instruction 5 minus 0 means from 0 to 5. Again, this is function. So what I'm saying is that LU knows how to do plus. LU knows, because if it receives 0 0, it means we're doing plus, and it can do plus. But when it receives 1 0, it just knows that, hey, in this case operation is controlled by the function. I need the function. What does this function mean? I need this function. So here comes our function from instruction at this range. So we are putting this value, we're passing this value to LU control. Okay, so that's why when our LU opcode is 1 0 1 0, the LU will find out that the operation is controlled by the function, and as soon as it will find out that the operation is controlled by the function, it will ask for this function. Hey, I need this function to perform the operation. So then we know that in LU control there is this instruction. It's a range 5 0, which is func in R type. I've shown you, right? In R type, this range in the instruction, in 32-bit instruction, in this range, func is specified. So this func is passed to LU control, and when LU will ask this func, will pass this LU control will pass the func automatically. Okay, so then this LU will execute the operation. So now actually you don't need everything, this kind of stuff, you see this, there's a func, right? Then you understand that the operation is controlled by the function. You just put 1 0 here, 1 0, but I explained to you briefly in details how this LU knows the function, how everything is controlled. So now you know everything. Okay, now you know everything, and you know why we put LU opcode 1 0, because in R type, again, the instruction is not specified by opcode, it is specified by function, which are passed at index 5 0 range. So when we pass LU opcode 1 0, LU in the table will find out that the LU needs the function, and as soon as it asks the function, LU control send the function to the LU. And how? Because LU control from here, this instruction from here already has beforehand the function. So this is the end of this video. I hope part B and C were understandable for you. If you have any kind of questions, just please feel free to ask in the comments, or in the comments of this video in YouTube, or in our Telegram channel, or contact me personally via Telegram. See you soon on next videos.